Today's topic is sets. If someone asks you what is a set, you can always say it is a collection of objects. This you can explain in the simplest words possible. What is a set? Set is collection of objects. Moving on to the second slide. The theory of set was developed by German mathematician and his name was George Cantor, and here is a picture. First, let us define what a set is. Set is a well-defined collection of objects. Now here they are talking about a well-defined collection. What does that mean exactly? A well-defined collection means that we can definitely decide whether a given particular object belongs to or does not belong to a given collection or not. As we have understood, it is a collection. First, let us talk about a collection of odd natural numbers. But there is one more condition, that these all odd natural numbers should be less than 10. So can we say that 1 belongs to this collection? Yes, because it is an odd number and it is also less than 10. Similarly, 3 is also odd number and it is also less than 10, and the same is true for 5, 7 and 9. Now let's take another example, collection of rivers of India. Now can we say Ganga can be part of this collection? Yes. Can we say Yamuna? It is also. Mahanadi, Krishna, Kaveri, Tapi, these all are part of this collection. But if I talk about Amazon River, the largest river in the world, is it part of this collection? I don't think so. Why? Because it is not part of India. Similarly, we can talk about Nile. It is the longest river in the world, but is it part of this collection? No, it is not. Now let's take a look at the third collection, which is vowels in English alphabets. We know there are 5 vowels in English alphabets, namely A, E, I, O, U. Now the thing is, we can see that A belongs to this collection, so does E, I, O and U. So we can say that all these are well-defined collections. Similarly, various kinds of triangles. If you take an acute triangle where all the angles are acute, if you take a right angle triangle where one angle is right angle and the other two are acute angles, or an obtuse angled triangle where one angle is more than 90 but the other two are less than 90. But can we say square belongs to this fourth collection? We cannot. Why? Because it is a quadrilateral and not a triangle. Similarly, for prime factors of 260, if you factorize 260, you will find that 2, 5 and 13 are the factors of 260 which are also prime numbers. Now 4 is also a factor of 260, but the thing is, it is not a prime number. That's why it does not belong to this collection. Moving on to the next slide. Now let us see some examples of collections. Sets means what? Collection of objects. Collections used in math. First of all, we have the set of all natural numbers. Now the thing is, if you look at the name of the collection, it is very long. So in order to represent it, what do we use? We use a capital letter. So natural numbers are represented by capital N. It means 1, 2, 3, 4 and the list goes on. They are all natural numbers. If we talk about set of all integers, then in this collection there are negative numbers, all the negative numbers from -3, -2, -1, including 0, 1, 2, 3, and so on and so forth. Now we have another collection, that is the set of all rational numbers. Rational numbers, please understand, it is P upon Q form, where P can be any number, positive or negative, and Q also can be any number. That is, let's say if you want P to be 15, it can be 15. If you want Q to be 7, it can be. So any number which can be represented in P upon Q form is a rational number. There is one exception. Q cannot be equal to 0, because if there is 0 in the denominator, and let's say P is 5, this is not defined. So that's why this does not become part of collection Q or set Q. Similarly, we have set of real numbers. It is represented by capital R. Any number you can think of. It can be a recurring, it can be a non-recurring, and non-terminating number. They all belong to real number. Like best examples could be root 2, root 3, root 5, even pi. They are all members of real numbers. Just so you understand, all these numbers are also part of real numbers. Similarly, we have z plus. Can you see this part? It means all the positive integers. It is same as integers, but they are only including the positive ones in this collection. Similarly, here is rational number, but only positive ones. Similarly, we can have q minus and we can also have z minus. Similarly, we have all the positive real numbers. Moving on to the next slide, we learned what were well-defined sets. Now let's learn some of the examples so that you can tell the difference between what are well-defined and what are not so well-defined. First example here is collection of 5 most influential actors. Now I have underlined two things here, subjective and varies from person to person. If you look at this collection, if you ask one person, his answer to this collection would be different from the next person. That's why it is a subjective case. Its answer varies from person to person. So you cannot say for sure if this member will be part of that collection or not. Similarly, if I talk about 10 best football players, again, its answer will vary from person to person. So it is a not well-defined collection or set. Next is collection of most dangerous animals of the world. Same thing. From person to person. For me, it could be shark. For you, it could be lion and other animals, right? So these are all not so well-defined sets. Moving on to the next thing. When you are doing sets, 3 points you have to keep in mind. First thing, we understood that set is what? It is a collection of objects. Now this objects, it has two synonyms. You can call it elements and you can also call it members. So that is, what is set? Set is a well-defined collection of objects or well-defined collection of elements or well-defined collection of members. So this covers our first point. Now here sets are usually denoted by capital letters. We saw in this slide that, can you see, natural numbers are denoted by capital N, integers by capital Z, capital Q. Basically any set, it is denoted by capital letters is what it is trying to say. Moving on to the next point, the elements of a set are represented by small letters. That is, when you are talking about the objects or elements or members, they are all represented by small letters, and the sets are represented by capital letters. Moving on to the next slide. Okay, can you see the symbol? It is a Greek symbol and it means belongs to. Similarly, if you put a cross on it, it becomes does not belong to. They have given here a collection of multiples of 5. Let's take those 3 points. Let's say I am representing this collection with a capital letter M. And this point we will come in a few minutes, that sets are enclosed within curly brackets. Okay, and all the elements or members of this collection, that is multiples of 5. 5 is a multiple of 5, 10, 15, 20, 25. They are all multiples of 5, and the list goes on indefinitely. So here you can see 5 is part of this collection. So I can say that 5 belongs to M. Can you see here I have written element which is inside, and here I have written name of the set. Similarly, I can tell for 15 that 15 belongs to M. But do you see the number 11 in the collection? No, right? So you can say that 11 does not belong to M. Similarly, I can talk about 26. Is it a multiple of 5? It is not. That's why 26 does not belong to M. I hope this clears belongs to and does not belongs to. Now, how many ways are there to represent a set? There are 2 methods. First method is roster, or you can call it tabular form, and second is set builder form. We will learn them in detail one by one. First, let us learn about roster or tabular form. I have underlined 3 things here: listed, separated by commas, and enclosed within the braces. Now, in roster, all the elements, you can also call them objects, or you can also call them members. So all the members of a set are listed, means you will see each and every element is written inside the set. Second thing is they are separated by commas. Can you see here I had used commas to separate each and every element. And the third thing, that they are enclosed within the braces. As I mentioned earlier, that here I have used these curly brackets, and within this curly bracket I have written all the elements and I have separated them with commas. Now we have 4 examples and I will explain you all of them one by one while keeping the 3 points in mind. Please remember, right now we are doing roster or tabular form. Now first example is odd natural numbers less than 10. I will represent this set by a capital letter O is equal to, then I will use curly bracket. Now 1 is odd number and it is also less than 10. Similarly 3, 5, 7 and 9. There are 5 members or 5 elements or 5 objects in the collection or set O. Moving on to the next, the vowels in English alphabet. Now here I will represent this set, the whole set, by capital letter V. Again I will open a curly bracket. I know A is part of this collection, so is E, I, O and U. Can you see all 3 rules? That set represented by capital letters. Then can you see it is, the elements are separated by commas, it is within the curly braces, and the letters or the elements are in small letters. Next is a set of letters forming the word balloon. Let's call this set L because we are talking about the letters in this word. Again, curly braces. Here, first I will write down B, then A, then L. Now see, here L is repeated twice. One very important rule, you should not repeat elements in a set. So I will not write L again. So next I will go to O. Again you can see O is repeated. In total it is twice in the letter, but I will only write it once. And the last one will be N. Again, there are how many? 1, 2, 3, 4 and 5. There are 5 members in collection L or set L. The last example, set or collection of even natural numbers. I will represent this set by capital letter E, and I shall start with 2, 4, 6, 8, 10, 12. Can you see this will keep going indefinitely? Now to represent the indefiniteness, I will use 1, 2, 3, 3 dots. It means that this list goes on and on. Moving on to the next method. This was all regarding roster or tabular form. Next we will learn about is set builder form. Here I have underlined important things, that all the elements possesses a single common property. Whichever element is in this set, they have a common property, and whichever does not have that property does not belong to this set. Again I will explain how to write in set builder form, and this is little bit trickier compared to roster, because roster you have to just list all of them. Here there is the minor difference. Now let's start with the last example. We saw that set of even natural numbers in roster, but in set builder it is little bit different. Can you see here I have represented it with capital E. If you see, this bracket I have highlighted in red. How do you read this? You read it as the set of all. That is it. You read it as the set of all. Then can you see X? Now this you read as element X or elements. My bad. So the set of all elements X. So what does X represent? It is an element in the collection E. Then you read such that. Can you see this colon? Colon means such that. Now how to read it? I know it's a little bit tricky because it is first time. You read this as the set of all elements X such that. Now this is what is the most important. X is a natural even number. So you ask yourself, is 2 a natural even number? Yes, then it belongs to E. Is 4 a natural even number? Yes, it is. So it also belongs to E. So here you do not have to list all of them. Instead, you have to use this method. Moving on to the next example, the vowels in the English alphabet. Again, what does this mean? The set of all element X such that X is a vowel in English alphabets. To be very frank, this portion is concerned for writing purpose. That is, you have to write it, but if you have to understand, you can only read this much part, that X is a vowel in English alphabet. Ask yourself, is A a vowel in English alphabet? Yes, it is. So you will write A belongs to V. Similarly, you can ask, is B part of English alphabet? Yes, it is. And is it a vowel? No, it is not. So this will not belong to V. Similarly, E belongs to V. I also belongs to V. Let's take X. Is X a vowel It is not. So it does not belong to V. Similarly, third, the set of all letters forming word balloon, but in which? In set builder form. Again, the set of all element X, such that this is the only portion that will tell you what it is, that X is a letter of the word balloon. So B A L O N, and my bad, it should be double O here. Moving on to the next example, odd natural numbers less than 10. Now here we have a conditional. Again, the thing is same, the set of all element X, such that X is an odd natural number. First, here it is saying that it is an odd natural number. So 1, 3, 5, 7, 9, 11, and the list goes on indefinitely. But they have put a condition here. Can you see that X, which was the element in set O, it is less than 10, which means that 1 will belong to O, 3 will also belong to O, so will 5, so will 7, and so will 9. So can you see all these belongs to O. Here you don't have to list it. That's why this is how you write. But can you say 11 belongs to O? You cannot. You have to write that 11 does not belong to O. Now let's see few examples, shall we? Now here, first one, it is saying write solution set of equation. This is x square plus x minus 2 is equal to 0 in roster form, they are saying. If I solve this, it is x square plus 2x minus x minus 2 is equal to 0. If I take out common, x will be common here, inside it will be x plus 2, and here minus 1 is common. So it is x plus 2 is equal to 0. So one bracket is x plus 2 and another bracket is x minus 1 is equal to 0. So I can take that x plus 2 is equal to 0 or x minus 1 is equal to 0. If I send 2 here, it will become x is equal to minus 2, and if I send minus 1 there, it will become x is equal to 1. Now let's say I want to represent this set with capital E, and I will write it in curly brackets. Here you can say that minus 2 and 2 belongs to the set E. Alright. Now they are saying write the set. Can you see this is given to us in set builder form and we have to convert it into roster form. They are saying the set of all x such that x is a positive integer. Now we know it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on and so forth. And they have given a condition that x square is less than 40. And we have to write this in roster form. Let's say I will use A to represent this collection. And as they are saying that x is a positive integer, it can be 1, 2, 3, 4, so on and so forth. But they have given another condition that x square must be less than 40. So let's say we are taking x as 1 and we will check the condition. X square will be 1 square, which is again 1. Is it less than 40? Yes. So it will become part of this collection. Let's go to the next integer, that is 2. Let's assume x is 2. Is x square, that is 2 square? The answer will be 4. Is 4 less than 40? Yes, it is. So 2 is also part of this collection. Now let's check 3. X is equal to 3. 3 square will be 9. Now is 9 less than 40? Please understand that this x square less than 40, whatever number we are getting here, this 9, 4 and 1, we are not supposed to write that. We are only writing this to check whether this condition is fulfilled or not. Now tell me, is 9 less than 40? Yes, it is. So 3 will become part of this set A. Similarly, 4 also will become part of this set. So will be 5, so will be 6. But when you come to 7, that x is equal to 7. X square, that is 7 square, will become 49. Can I say that 49 is less than 40? I cannot. It will be false. That's why it has 1, 2, 3, 4, 5 and 6 as its members. One more important thing I want you to understand, if I say that there are 6 members in set A, I can write it as n in small brackets A is equal to 6. This means that number of elements in set A is equal to 6. Similarly, if you look at here, how many elements are there? 2. So I can say that number of elements in set E is equal to 2. I am only counting how many elements are there. Moving on to the third one, you can see, right, the set A is equal to, now here they have given the example in roster or tabular form. Yes, and we have to write it in set builder form. Now you can see this, it is 1 square, 4, it is 2 square, this is 3 square, this is 4 square, this is 5 square, and it keeps going indefinitely. If you can sense a pattern here, everywhere you can see it is square, right? And here you can see number is increasing by 1. Wait a minute, let me write all this again. 1 square, 2 square, 3 square, 4 square, 5 square and dot dot dot. Now here square is common to all the elements, and from one element to next you can see there is increment of 1, again 2 to 3 increment of 1, so on and so forth. So how will we write this? Capital letter A, the set of all x such that x is equal to n square. Now this is very important, I will explain you what it is. I will do a semicolon to separate it and I will write that n belongs to capital N. Now this is very encrypted, you will think. It is. Now the thing is, I have said that the set of all element x such that x is equal to n square. This is the first thing. X is equal to what? It is n square. But then I have given little more details on what n is. N belongs to capital N, which means every natural number can be n. So here, can I take n is equal to 1? Yes, because 1 is a natural number. So I will write x is equal to 1 square. Therefore, x will be equal to 1. So here, can you see, we got the first element. Similarly, again, can I write n is equal to 2? Because n belongs to natural numbers. But n is connected to x is equal to n square. Again, I will have to apply that formula. So here I will write 2 square. So x will be equal to 4. So understand why x, it is element of set A. So here we have to write whatever the x is. We got the second element, that is 4. Similarly, I will take n is equal to 3. So it will be x is equal to 3 square, which will equal to 9. Again, we got the third element. Similarly, you can even take n is equal to 10, for example. Okay, so it will become x is equal to n square, which is 10 square and which will be 100. Now 100 is also, that is 100 also belongs to A. Why? Because here it goes on indefinitely. So it is basically set of squares of natural numbers. Moving on to the next one. Write the set. Here they have given it in roster or tabular form and we have to write it in set builder form. So I will write down, let's call this set C, for example, and I will write the set of all Now elements in set C is x, so I will write down set of all x such that x is equal to n upon n plus 1. I will explain what this is. If you can see here, the numerator, this is 1, and you can see the denominator, it is 1 plus than the numerator. So let's assume, I will write down one more condition, that n belongs to n, that is natural numbers, and I will add one more condition, that n is less than or equal to 6. Okay, first let us discuss what small n can be. Now they are saying it can be a natural number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but they have given another condition that it should be either equal to 6 or it should be less than 6. So it can be 1, 2, 3, 4, 5 and 6. Then I have taken this as my formula, that x is equal to n upon n plus 1. Let's assume that n is equal to 1. So I will write it as 1, and below I will write it as 1 plus 1. So we will get 1 upon 2. Can you see it is the first element? Similarly, let's assume that n is 2. So x is equal to 2 upon 2 plus 1. So it will be 2 upon 3. Can you see it is the second element? Similarly, let's assume that n is 5. So x will be equal to 5 upon 5 plus 1. So it will be 5 upon 6. So we get this element also. Similarly, if you apply 3 and 4, you will get these two elements. Let's move on to the next one, that x is equal to n upon n plus 1. Now let's take n is 6. So it will be 6 upon 6 plus 1, which will be 6 upon 7. And now here it ends. Why? Because n is either equal to or less than. Can you take n is equal to 7? You cannot. So this set is completed here. Thank you for watching.